So today we have Anthony Speranza from Perimeter. He's going to tell us about anomalies in gravitational charge algebras, no boundaries, and black hole entropy. So yeah, thank you, Anthony.
Okay, yeah, thanks a lot for inviting me to give this talk. So I'm going to be talking about mostly about this. Can we see this? Yeah, mostly about this paper that I just put out in September with Ben Chandra-Sakarian, who's a grad student at Berkeley, so you guys should know him. And also this work from a little earlier this summer with Linqing Chen and 3 master's students at PI, Wenjin Chua, Shui Liu, and Bruno Torres. And it's kind of nice, even though we have to be virtual and all of these things, it's allowed us to do this thing where Ven gives a seminar at PI on the same day, right before I give a seminar on, at his place in Berkeley. So that's been a nice bonus. So anyways, yeah, so the thing I'm going to be talking about today is basically, it goes under this general idea of charge algebras at boundaries and what you can learn about black hole entropy. So as the title suggests, we're interested in null boundaries, and these come up when you're doing general relativity. They come up all over the place. Some examples are, you know, when you're doing asymptotically flat space, scribe plus is known to be a null boundary, and this could give you some, you know, the properties of that could be interesting for developing flat space holography. Things like event horizons for black holes, talking about things like entropy bounds and quantum focusing conjecture, you're often dealing with null boundaries. Similarly, Cauchy horizons in general, like, you know, bounding something like an entanglement wedge, again, are null boundaries. So they come up all over the place in GR. And one of the things you can do is you can look at these, what I call quasi-local charge algebras that show up on these null surfaces. And these are just charges that appear because you've introduced a boundary into your system. So things like understanding bonding mass in asymptotically flat space and how that decreases due to gravitational radiation, things like gravitational wave memory. But the thing I'm mostly interested in this talk is this idea of something like edge modes or soft hair on a horizon like a black hole event horizon. And in particular, I'm interested about what you can learn about the black hole entropy and maybe possible microstate interpretations of that, like what these edge modes say about microstates. Okay, so kind of one of the philosophies I have for why these charge algebras associated with boundaries are related, have anything to do with entropy, kind of comes from this extended Hilbert space construction and entanglement entropy. So I think it's a well-known fact that there's kind of some tricky aspects of defining entanglement entropy when you have gauge symmetry in a system. So the basic idea is entanglement entropy would be like associated with some subregion sigma. This is like a spatial slice, and then you cut it and it has a little red boundary here. But when you have gauge symmetry, you have like non-local observables that are like Wilson loops. And if they cross the boundary, there's no sense in which that Wilson loop can be associated either with the subregion or its complement. And this is just saying that the Hilbert space doesn't really factorize the algebra, you know, associated with one region isn't just the tensor factor with the other to give you the full thing. And so the idea of the extended Hilbert space is you introduce edge degrees of freedom. Here I've shown these as these pink little dots, which you can think of as little charges on the end of the Wilson line. And you just introduce these extra degrees in freedom in order to force the Hilbert space to factorize. And then you can, you know, you want to embed the physical Hilbert space inside this bigger extended Hilbert space, and then which does factorize, and then ask about entropy. So there's this, in gauge theories, there's this nice formula by Donnelly where if you do this, you can kind of write the entropy as something that looks like a von Neumann entropy kind of associated with each sector associated with a specific value of these edge charges, plus, you know, an extra piece that might look something like the expectation value of an operator. And it might have some, in a gravity theory, it could, you know, look like this would be basically expectation value of an area. So it's kind of a conjectural picture, but it's sort of the philosophy I have in mind with these charge algebras. They appear as a way to allow a non-factorizable Hilbert space to factorize, and the entanglement between the extra degrees of freedom that you introduce to make it factorize can contribute to the entropy. And so just to point out, this formula I think is most rigorously defined in gauge theory, and in particular probably lattice gauge theory. But there's been some analyses on what you do with gravity. It's a little more complicated because the symmetries are more involved, but there was this nice work by Donnelly and Friedel talking about how you do it classically. I've done some work on some like the higher curvature generalizations, and I'm working with Donnelly, Friedel, and Mousavian on aspects of how you would quantize the resulting symmetry algebras. So this is more just like morally the idea that I have in the back of my mind, but really what we're going to focus on are a slightly different class of symmetry algebras. And it's sort of so you're going to look at symmetry algebras that basically contain some sort of Virasoro factor in the hope that you can actually kind of nail down the exact coefficient, get an A over 4G from some sort of edge interpretation. So this story is familiar from the first time this, using Virasoro symmetries to fix the entropy, I think was this paper by Strominger. It's well known for asymptotically ADS3 spacetimes. He found the Brown-Hinault central charges can be computed. And Strominger noted that when you apply the Cardy formula with those central charges, you reproduce the BTZ black hole entropy. And this kind of thing, and so Strominger also, I think, mentioned in this work that he thinks anytime there's kind of a near horizon ADS factor, you could do something like this. And Carlip showed fairly explicitly that you can do this for pretty arbitrary killing horizons. Another kind of manifestation of this type of construction comes from this Kerr-CFT correspondence, which was specifically done for extremal Kerr spacetimes, and you get a sort of ADS-like factor in the near horizon region. You could work out near horizon symmetries and find these Virasoro algebras. And there, similarly, they note there's some sort of Cardy formula that seems to give you the Kerr black hole entropy. The real problem that Ben and I were interested in, and that'll be the main topic of this work, was this work by Hako, Hawking, Perry, and Strominger related to this hidden conformal symmetry as well by Castro, Maloney, and Strominger, where they were trying to look at basically, are there aspects of this Kerr-CFT correspondence that applies for just regular Kerr that's not extremal. And they similarly were trying to write down near horizon Virasoro symmetries and see if those had a relevance to the black hole entropy. And so this paper that I put out earlier this summer with these collaborators, where we were looking at their construction, and also we extended it to a much larger class of horizons, where we said all you really need is to have any killing horizon with a rotational symmetry associated with it. But basically what the whole philosophy of these constructions tends to be is you want to find one or two copies of a Virasoro algebra with a central charge computed from these classical commutators, these classical Poisson brackets, similar to what was done in the Brown-Hinault construction. And then you're going to apply the Cardy formula to the resulting central charges. And that's given by this formula, and you hope at the end that you get an area over 4G. And this sort of suggests that these charges that you're writing down might be a classical manifestation of, a quantum CFT description, just because Virasoro is the symmetry of a CFT. So as I said, we're interested in this HHPS and generalizations of that construction. And it's kind of interesting from this quasi-local charge perspective, essentially because the charges they considered are what I would call genuinely quasi-local, or sometimes it's called non-integrable. So what that means is, in standard constructions, say by Carlip, you generally have a horizon, and then you start imposing boundary conditions on the horizon. And these boundary conditions are supposed to make whatever transformations you're considering kind of integrable. So you have a closed system associated with the external region. This is sort of a little philosophically incongruous with the idea that all you're really trying to do is split your space-time into a subregion and its complement, because boundary conditions really give the boundary the status of a physical barrier. They prevent flux. So it's not very natural when discussing a subregion. And so in general, you might want to have a description where you don't really impose the boundary conditions, but you can still measure these charges and fluxes. The other reason this is important for this specific class of transformations that HHPS considered is that there's not really a local boundary condition on the horizon that you can impose to make the charges integrable. Basically, any sort of local boundary condition is going to kill the degrees of freedom that you're interested in. Okay, so for those reasons, we had to consider this more general construction that goes under the name Wald-Zoupas, which is a way of constructing charges that aren't really conserved, but it's something that is almost conserved, but you can allow fluxes into a complementary region. And so it's just kind of thinking about open systems canonically. So the goal was just to systematically understand this, but it turned out there were certain aspects of the Wald-Zoupas construction that we actually had to generalize or clarify in order to carry out this procedure. There's sort of three problems that come up when you're dealing with these quasi-local charges, and these are the things that we looked at in this paper. The first is that there's kind of an ambiguity in determining what you call the charge and what you call the flux in the Wald-Zoupas procedure. And there's been various proposals for how to fix this ambiguity, but the important point is that this is sort of 100% essential for the final result you get for the entropy. Your different choices on this ambiguity almost entirely determine this, this value for the central charge. And we're going to see that explicitly in the analysis that I show you. So we have to come up with a way for fixing that ambiguity. The second point is you just need, once you have these sort of non-integrable charges, you don't really have a Poisson bracket available to define your algebra. So you just need to confront the problem of how you define an algebra for the non-integrable charges. And then the third point is just we have to really carefully think about how you do this construction on a null boundary without imposing overly restrictive boundary conditions. And so this was just something we had to reconsider carefully because previous constructions impose one boundary condition or another that all turned out to not work with the problem we wanted to solve. So basically, the goal of this talk is to show how these three things are resolved, and actually resolving them, I think, clarified a number of things about this Wald-Zoupas construction. So I think it was a useful exercise that Ven and I carried out, and I think it helps, just clarify aspects of the construction. And then once it's in place, we can analyze the Cardy formula and try to get an entropy out of the final result. One of the things, though, that I want to focus on is this concept of why you get central charges in general from doing this sort of thing. And the whole idea is that we're going to really be looking at this anomaly interpretation of the central charge that appears. So roughly, we're going to look for a relation like this where you have some bracket of charges is equal to, the charge associated with the bracket plus an extension that we call K. And we want to connect this K to a type of anomaly that's occurring. And so this anomaly appears in the case of null boundaries because we have chosen a boost frame for the null normal. So that just means that the null normal, L lower, generally is thought to have this rescaling symmetry since null vectors don't have a preferred normalization. And we want to argue that a choice for this rescaling symmetry is analogous to a choice of a Weyl frame in a CFT. So this is like, similarly, the metric kind of has a rescaling symmetry when you're talking about CFTs. And that we want to show that this choice of frame is what's giving rise to these extensions. And I think this is, and then interpret that as a type of an anomaly. And this may help clarify a sort of strange aspect of this, general Cardy-ology construction, is that there's like many different symmetry algebras that people have written down over the years. You have Virasoro, BMS, warped CFT type things, Heisenberg, etc. And they all seem to have some kind of Cardy formula that gives the entropy at the end. And one of the things we want to try to argue for is that maybe the specifics of which algebra you're using isn't the important feature. It's really this anomaly that you compute that might be the universal feature. So I'll try to point out where this shows up throughout the talk. I'm going to go right ahead and start addressing the 3 points I mentioned, but I guess I can pause to just see if there's any questions before that.
I guess my question is, are you restricting to a fixed background with a killing horizon, and you're analyzing matter fields on this background, or what is the precise setting in which you're operating?
So in the example that we're going to consider towards the end, it's actually going to be vacuum GR with a killing horizon background. The stuff that we develop in the interim can be applied much more generally. So we'll show some general formulas that work, however you determine how you want to specify a null boundary. So it certainly, some of the applications from this work could be looking at other types of subregions, but the specific application is for killing horizons. Okay,
but so what I should have in mind as I follow along is really an arbitrary null surface, which might have caustics and so on.
Okay, yeah. I think caustics are probably a good question. We're essentially, I think a lot of it ends up being fairly local near, say, a codimension 2 surface. So you can sort of do a lot of the analysis before caustics forms.
What does it mean to be near when you're going along a null direction?
So pick any, caustics form within a finite affine parameter, take some affine parameter, there's always a finite distance before caustics form, right? So for example, that. So
in principle, this is an expansion in the expansion?
Oh yeah. Yeah, in some sense, I'm just saying a lot of the analysis you can do right next to the surface. I think the question of caustics is probably a really interesting one. It's just not something we considered here. But yeah, more or less, you think of just start with a codimension 2 surface. You can probably do the analysis just barely moving off of that surface in the 2 null directions. Okay. Hopefully, yeah. Feel free to ask if you see a spot where the caustics could lead to problems. I think it's an interesting question. So, okay. So the first step is just to talk about this Wald-Zoupas construction. And just to be completely general, we're not even going to talk about null surfaces to begin with. We're just going to explain how this works in general, because the formulas we derive, I think, are pretty universally applicable. So it would work for time-like surfaces at this point as well. The specific tool we're going to use for this is covariant phase space, just because I find it convenient for the canonical analysis. Sort of plays nicely with the diffeomorphism symmetry. But just to give a lightning review of the essential features here, one of the things that you use in covariant phase space is this symplectic potential current called theta. And this is just the boundary term that shows up when you vary the Einstein-Hilbert action. So you can see it involves variations of the Christoffel symbols. And it's the thing that you're going to use to construct a symplectic form. The other thing that appears all over the place is this another potential. Because gravity has diffeomorphism symmetry, you construct another currents that are conserved on shells, and hence can always be written as the derivative of a potential. And that's what this Q is. And so you write down, when you're talking about a subregion, you want to construct a phase space, you need a symplectic form. It just comes from the antisymmetric variation of this potential integrated over the Cauchy surface. And what this thing does is allows you to construct the charges associated with a diffeomorphism. And those charges are supposed to satisfy Hamilton's equations, where the variation of the Hamiltonian on shell is equal to this symplectic potential evaluated on, you know, the transformation of the metric. So here I'm doing vacuum GR at this point. And the reason for this, so then there's this identity that this standard Dyer-Wald identity that on shell, this localizes to a boundary integral. And the reason there's a question mark here is that it's not clear that this second term is a total variation. And so this is where the concept of a quasi-local charge is going to come in, because if this isn't a total variation, you have to come up with a way to split off the total variation piece that you call part of H and then another piece. So just to give you a kind of a picture of how to think of this, you've got some open subregion U. Here I've drawn it as bounded by this null surface N. I've drawn it as a null surface, but again, at this point, it could be a time-like surface as well. And here I've drawn sigma, the Cauchy surface. It's just like a spatial slice, and I've drawn it here to even include part of the null horizon, as you are free to do. And so what you want to do is, to construct this H, is you want to kind of split off the total variation piece. So you decompose theta into what we call a boundary term, the corner term, and the flux term. And so here we're constructing charges associated with this diffeo Xi. The reason for this terminology kind of comes from the variational principle, and I think this was most explicitly communicated in this work by Harlow and Wu, where this L actually is closely related to the boundary term that you add to the action in the variational principle. So when you vary the bulk action plus the boundary action, you get integrated over the bulk equations of motion. And then this flux term is all that's left that's integrated over the boundary. And then this beta here kind of localizes to the corner term in the variational principle. So that sort of explains what that terminology means. And so if you want the variational principle for the subregion to be well defined, you need to come up with boundary conditions that set the flux to 0. And if you do that, you can write down these charges. So more generally, the Wald-Zoupas procedure says just like ignore the flux piece and construct the charge as if this were 0. And you get this formula, which with the corner corrections that Harlow and Wu identified is just given by this general formula. That's a sum of the Q plus the boundary term plus this corner term. So this is great. The only issue is this decomposition here is not unique. And the non-uniqueness is kind of essential. Like I can always move a piece of this L into the flux because I haven't told you anything about what this flux is. So in order to fix this ambiguity, I really need to have a principle for fixing what the flux is. So the thing we proposed in this paper is that this flux should really be of Dirichlet form, which means we want it to take the form of variations of intrinsic quantities times, conjugate momenta that might be constructed from things like the extrinsic curvature. And so imposing this Dirichlet form largely resolves the ambiguity of splitting into a total variation in a flux piece. There's some caveats that I think are most relevant when you're talking about asymptotic symmetries, which I can, if you want to ask about it towards the end, I can tell you more about that. But we'll find for finite boundaries, this essentially fixes the form of the flux. So just to give some arguments for Dirichlet, this is what you do in the Brown-York construction for quasi-local charges. And it gives these conjugate momenta the interpretation of like a Brown-York stress tensor. By the way, I've written this in terms of this variation of this null vector as well, because this is the form it would take on a null surface. On a time-like surface, you just have this first term. So we'll see explicitly what these are later. The second reason is that this is kind of a familiar thing that you do in holography, and this is also just related to the Brown-York interpretation, where you sort of fix the values of the fields on the boundary, and then you interpret the conjugate momenta as your operator's expectation values. And those are the things that have can fluctuate. We have another argument in terms of gluing subregions together. So if we assume that we have sort of a subregion and we want to eventually attach on the complementary region to get the global spacetime, the Dirichlet form here seems to be preferred using the following argument. So when you do the Dirichlet form and do the variational principle associated with a subregion and its boundary, you're going to kinematically match the intrinsic quantities that are appearing here. And then the variational principle then kind of dynamically sets the conjugate momenta to 0. Or if you had like an actual distributional stress tensor there or some sort of brane, this would be set equal to the distributional stress energy. But like in a path integral where you're looking at off-shell configurations, this form of the flux ensures that the metric is continuous across the surface, even in the path integral. In the Neumann matching, where you kind of kinematically match the extrinsic curvature, your off-shell configurations now involve jumps in the metric, which is quite a bit more singular than allowing jumps in the extrinsic curvature. Jumps in the extrinsic curvature are associated with things like conical singularities or defects, but jumps in the intrinsic metric, it's sort of distributionally ill-defined curvature. So for this reason, we're going to argue that the Dirichlet form is the preferred form when you're constructing these quasi-local charges. And it's the one that we'll focus on for the rest of this work until the very end, and we'll see exactly where we consider some possible different choices. So finally, the last property that these charges satisfy that makes them kind of useful is that they're no longer conserved due to the fluxes. But the Wald-Zoupas procedure instead kind of constructs a continuity equation where you construct the charges on, say, like 2 cuts of the null horizon, and you realize that there's some flux of the charge, out of the subregion, and you can relate the difference in the charges here to the flux. So that's what this curly E represents. But you can see already that what I said is not entirely true. I showed that there's like another term that appears in this flux equation, and we want to interpret this as kind of an anomalous violation of the continuity equation. So this delta C L, so remember L is the boundary term in the action, and this delta C is measuring the failure of L to transform covariantly under a diffeomorphism. So this first term is just how it transforms when you vary it using the rules in the action, and leak C is just a covariant transformation law for it. And so here, this continuity equation actually looks like it has a violation due to flux of charge and also an explicit violation. And so we want to start interpreting that this non-covariance of the boundary term is really acting like an anomaly. So you can think of this as being analogous to an anomalous word identity, where there's an explicit violation of a conserved current. So this is the first place where we see this anomaly popping up in the construction. Okay, so the second thing we have to do is just define the algebra for these quasi-local charges. So the reason this is a little non-trivial is that, again, the charges aren't integrable, so you don't immediately get to use the Poisson bracket. Basically, they're not conserved charges because you're losing fluxes. But this problem's been considered before in this work on the BMS charge algebra by Barnich and Troessaert. And they defined this modification to the bracket where you would take the variation of the charge and you correct it by this flux term. And so this is what we'll take as the definition. And it's a really useful bracket because you can prove basically a charge representation theorem, which just says that the brackets of your charges is equal to the charge of the Lie bracket up to an extension. In general, this extension, so normally in symplectic geometry, you have central extensions that appear here, because we're considering a slightly different bracket, we have what's known as an abelian extension, where you could have multiple values for this k, and the h's can transform the k amongst themselves, but the k's commute.
Anthony,
yeah.
can I ask a question?
Yeah.
Can you hear me?
Yep.
Is that modification of the bracket, does it amount to a change of the symplectic form? Does it correspond to a different symplectic form?
It doesn't come from a symplectic form. It doesn't entirely come from a symplectic form on the subregion. So, I mean, it looks basically like, it looks kind of like omega evaluated on leak CG, Lee zeta G, plus something that involves these flux terms. Okay, is what it works out to be if you work out what this delta CH is. So it's like a correction to the symplectic form. And the way we want to interpret it is really, the way you would probably derive this is basically glue on the auxiliary system, construct a Poisson bracket kind of on the global system, and then work out what it ends up being for these quasi-local charges, which are just functions on a subregion. But basically, there's not like a principal derivation in existence. There's some work by Troessaert that interprets this bracket in terms of what he calls external symplectic symmetries. But yeah, it doesn't exactly come from a Poisson bracket. I guess one thing I could mention is if you come up with boundary conditions to make the charges integrable, this bracket does reduce just to this Poisson bracket, which is just this one. So it's sort of just a generalization to the non-integrable things, but you can always, it will become the Dirac bracket if you find boundary conditions to make your charges integrable.
Thanks.
Okay, yeah, no problem. Okay, so I mean, in the examples that we're working with, we're gonna find central extensions. This abelian extension might be interesting in other algebras, but for now, you don't have to worry too much about it. But the other thing that we did in this paper was write down this general formula for the extension that appears. I think this is, I don't think I've seen this formula for the extension, the central extension before. Maybe someone will tell me they've done this before, but I think this is, really does this, really emphasizes the role of the extension as an anomaly. So here we see that this K term comes entirely from the failure of the boundary term to transform covariantly. So this delta C, again, was the measuring the extent to which L is not covariant. And again, this formula will apply if you have integrable charges. So it sort of quite generally is going to be true that central extension always has something to do with a non-covariant boundary term. And this kind of brings the analogy to holographic Weyl anomalies to the forefront, because there you're considering a slightly different setup where you're writing down kind of a radial cutoff in asymptotically ADS. And then you have to start writing down boundary terms as sort of ways doing this holographic renormalization. And it's known that holographic Weyl anomalies appear from, you know, various non-covariance properties of those boundary terms under kind of the radial reparameterization. And so this formula is quite analogous to that. And it's sort of saying anytime your boundary term has this anomalous transformation, you can get an extension. Okay, so that concludes the charge algebra piece. The last thing that, I guess I can pause real quick for questions. Okay. So the final thing we have to do is just apply this now to a null boundary. So everything I've said to this point is fairly general, but now we need to specialize for the null boundaries, which we're interested in. And so as I think I mentioned before, what we're going to do to specify a null boundary is really, we just want some surface n, and we're going to fix the normal vector to that surface as kind of a way of saying where the surface is. And so we're going to impose that L downstairs is fixed. In order for it to impose that it's null, we also have to say, you know, L.L is 0. And this has the effect on the variations of restricting the metric variation somewhat. But then the point is, we're not going to impose any other boundary condition on the metric variations, basically for the practical purpose that it's not compatible with these symmetries we're interested in. So on a null surface, the intrinsic quantities are the metric pulled back to the surface. So that's just this degenerate metric that appears on a null surface. And L upstairs is now tangent to the surface. And so that is the other piece that we consider the intrinsic geometry. The extrinsic geometry, essentially, you construct from this shape tensor. That's just the covariant derivative of L upstairs. For a time-like surface, this would essentially be the extrinsic curvature tensor. For a null surface, you sort of, it's slightly different. You split it into a piece that's like the extrinsic curvature, so K downstairs, and it's really like an extrinsic curvature of the codimension 2 surfaces foliating your null surface. And then you have something called the Hadricek 1 form, which measures something about the rotation of the horizon. And K is your inaffinity, which is just the failure of L to be affinely parameterized. I should mention that this sometimes goes by the name kappa, and sometimes people will call it surface gravity because on a Killing horizon, all the definitions of surface gravity are the same. We found it useful to call it something different, just because the different ways of defining surface gravity on a null surface differ, basically, if you're on something besides a Killing horizon. And there's a different definition that's a bit more closely tied to the role that kappa plays as the temperature. So just as an aside, this K is equal to kappa in the background, but its variation is different. Okay, so then I can show you this decomposition of theta into this boundary, corner, and flux piece. So the interesting piece is this boundary term in the action here. So it's constructed from this inaffinity. And so this has been written down before, but fairly recently, these works by Paratu and Lehner, people who are interested in like complexity, were really interested in properties of boundary terms at null boundaries. So this is the guy that shows up in those things. The other thing that's kind of interesting out of this decomposition are these pi ij's and pi I, just because this is the analog of a Brown-York stress tensor on a null boundary. And so you can see this kind of has the form of, you might expect of, you know, the momenta conjugate to Gij. It's just that K and theta are kind of different components of an expansion. So these don't play a huge role in what we're doing for the rest of this, but I think these are an interesting thing to think about if you're interested in something like horizon holography or flat space holography. I think these things, you know, since the Brown-York stress tensor really is the stress tensor in holographic setups, these would be interesting to look at. Okay, but the thing we need for this talk is this boundary term, and so the thing we need to compute is how this transforms under Diffeos. So since we fixed L downstairs, it's the one thing that's going to cause non-covariance to appear, and it's the only thing that we fixed. So this Lie derivative of L downstairs, as long as C preserves the horizon, is just proportional to L downstairs. And then you can compute this non-covariance just because this first term is defined to be 0. And so all that's left is leak CL. And so it's just this function W determines the non-covariance. So because we fixed L downstairs, we've introduced some sort of anomaly, and then we can compute the anomalous transformation of the boundary term, and it's just given by the derivative of W. So this formula is going to be really useful now in our example, where we want to analyze the Killing horizon. Maybe as a final note on this construction at null boundaries, is the way trying to connect this fixing L to a choice of Weil frame. So there's another way you can think of this choice of normalization of L is you can think of it from this stretched horizon perspective. So if you think of a bunch of time-like surfaces that are sort of foliating the near horizon region and asymptoting to the null surface here, the gradient of like the function that determines those surfaces will become like the null normal of the horizon. And if you pick two different ways of choosing the stretched horizon here, I've got the pink foliation and the green foliation. These will basically rescale L. So if you just do a refoliation where you don't actually change the leaves, all it does is rescale L by a constant once you evaluate it on the null surface. And that doesn't really have a big effect on anything. But if you actually change the stretched horizon, so you have a different sequence of surfaces, it rescales L pointwise. And this should be familiar to what happens in holography, where if you change your radial cutoff, that's a way to go between different Weyl frames because you can change the induced metric as you go out to infinity. Okay, so this is just another way of thinking of this anomaly that appears as really analogous to a Weyl anomaly. So that kind of concludes the formal aspects of the construction. So from here, we're going to move on to the null, the killing horizon, unless there's any other questions. So I'll pause for a second. Okay. Okay, so as a sort of an application of this general formalism that we set up, we wanted to analyze basically these symmetries that were considered by HHPS for kind of near horizon conformal symmetries of Kerr, and also these symmetries that were generalized in this paper by myself and some collaborators this summer to arbitrary axisymmetric killing horizons. So axisymmetric just means you have this rotation vector that I'm calling psi here, and it just means that it has like closed orbits on the horizon. So you can think of the horizon as being foliated by a bunch of circles coming from the orbits of this rotation killing vector. And so what you do is there's sort of a universal form of the metric near any such killing horizon. What you can do is construct canonically this dilatation vector, which we call rho, coming from the gradient of the horizon generator. So sorry, yeah, LA is going to be the killing horizon that's tangent to the horizon. Rho is going to be the gradient and psi is the rotation. So you should think of L as like a boost generator at the bifurcation surface, and rho is like a dilatation at the bifurcation surface. So just to draw that, L is kind of like this, and rho would be something like this, just to give you a picture of what that looks like. Oops. Okay. And so what you can show is that when you look at the metric using these guys as basically your coordinate vectors, you can show that the metric takes this near horizon Rindler form, where the first factor, so x is like a radial coordinate and t is the parameter along L. It takes a Rindler form times a transverse, and then there's some subleading pieces associated with the rotation of the horizon. And so what HHPS did and what we generalized in this work here was they looked for what they called conformal coordinates. There's sort of this weird twisty coordinate system where it depends on these two parameters, alpha and beta, and you sort of exponentiate e to the alpha phi plus kappa t and beta phi minus kappa t. And so here I've drawn the horizon and a surface where w plus and w minus are constant, and it kind of spirals in towards the bifurcation surface. And what these coordinates do is they make the metric expansion look like it has an ADS3 factor up to subleading corrections. And so now you're sort of foliating the near horizon region by these ADS3 folia that kind of wrap around near the horizon. And so the HHPS vector fields and the ones that we wrote down were constructed to preserve this structure. And so here, at this point, alpha and beta are just two parameters that we've associated with the construction. The original paper had some specific choice for these temperatures, but one of the things we did was show that basically any choice of them, and sorry, yeah, we're gonna relate them to temperatures in a moment. And so one of the things we showed is that these are essentially free parameters associated with the construction. Okay, so what you can do is write down the vector fields that basically preserve this ADS3 factor. Unsurprisingly, you get a diff S1 times diff S1 algebra. And so that just means you have two copies of the wit algebra, Xi and Xi bar, and these two copies commute with each other. And so it's useful to re-express them in this original coordinate system with the, the boost, the dilatation, and rotation here. The reason is it's when you express it in this basis, the component proportional to the dilatation ends up being the thing that determines your anomalies. So what we showed in the paper is that it's literally the coefficient right here that determines this WC. And that really simplifies. There's one of the things that is usually a bit mystifying about these calculations is that you do a lot of work to compute these brackets, and in the end you get something really simple. But this way of looking at it ends up showing immediately that it's just, this coefficient that's affecting the result. Okay, so we're almost done with that procedure. We've computed this function WC, and we showed before that essentially the derivative of WC is what it determines the central charge. So you can just compute this quantity here using the formulas that we found and extract an extension of this wit algebra. So you get two copies of Virasoro. The central charges end up being equal, and they're given by this formula 3a over pi g times alpha plus beta. Okay, so we're basically one step away from getting our entropy formula. The thing we have to do is so now we want to apply the Cardy formula. And this is where this choice of temperature is important. But basically, you can show that alpha and beta are literally just the left and right temperatures. You look at what this Frolov-Thorne vacuum is doing near the bifurcation surface, well, near the null surface, but really near the bifurcation surface. And all this vacuum is the thing that's thermal with respect to this boost parameter. So it's kind of what you expect the near horizon vacuum to be. And when you look at that and decompose into the L0 and L0 bar modes, you identify these parameters as the temperature. And then the canonical Cardy formula, now you just apply it, it's C times T times pi squared over 3. And so we come to this sort of surprising result that the algebra and central charges that we compute gives twice the entropy of the horizon. Okay, so this was almost the result we wanted, but this factor of 2 is sort of quite important because that's one of the things is that A over 4G is the correct entropy. So we sort of have, I'm going to just give it the explanation that we have for this factor of 2. And I'll give also a contrasting setup where you don't get the factor of 2. But this, I think explaining fully this factor of 2 is something that would be good to look at in the future. So the thing that we said that this factor of 2 possibly could be telling you about is that we have this picture of quasi-local charges, but really this being associated with an open subsystem that's kind of exchanging fluxes with a complement. And because this BT bracket probably comes from a Poisson bracket on this global system, it may be that when you impose this Dirichlet form for the flux, the charges that you write down for that are really computing basically a set of generators associated with the subregion and its complement. And the idea is you would have sort of a set of edge modes associated with your one subregion, sigma r, and the edge modes are kind of at the boundary here. You have a complementary region that you're going to glue onto it, which is sigma L and the edge modes. And if for some reason this bracket was computing the central charge associated with, you know, edge modes of the right CFT and edge modes of the left CFT, you would just get, you know, the central charges would add, you would get twice the central charge. So now if we imagine this setup where in this gluing procedure or this extended Hilbert space procedure, you basically entangle the edge modes, and that entanglement in holographic setups is supposed to, you know, build up the interior geometry. So here I've drawn it basically from a stretched horizon perspective, but you could also imagine taking the limit to the bifurcation surface where essentially you're gluing right across the surface. So if this was what this bracket were computing, and then we simply applied the thermal Cardy formula, you end up getting a factor of 2 because the Cardy formula assumes that the global state associated with both guys is just thermal. And so that's just going to give you twice the entropy. And the idea is then if you traced out the left-hand side, the entropy associated with the right would be down by a factor of 2. Similarly, if you thought this guy was in a thermal field double, this tracing procedure would again give the right guy in a thermal state. And again, you would get the factor of 2 gone. Okay, so this was a proposed resolution. One other thing that we did though was consider what would happen if you had something like a closed system. And in that case, what you do this thing where you need to find boundary conditions that ensure that you're not losing flux between the two spaces, and then you're sort of in a more standard setup. And so we can turn to that as a way of contrasting with this this gluing procedure and the Dirichlet. Excuse me. So another interesting result was if you wanted to find integrable generators, there's sort of 2 requirements. You need these parameters alpha and beta to satisfy this relation that their difference is given by basically the ratio of the horizon angular momentum in the area. And you also find that the boundary term in the action that gives the integrable generators is down by a factor of 2 from the Dirichlet form of the generators. So that what that means is now your central charges come with an additional factor of 2 in the denominator, and since the entropy depends linearly on the central charges, you're going to get A over 4G when you compute the Cardy formula. And in this case, you can do a little bit better because now you can compute the values of the 0 mode generators, L0 and L0 bar. They're both proportional to the area in this setup, and this requires both of these conditions when you compute it, in particular, the special choice of temperature. And in this case, the microcanonical Cardy formula ends up being valid here. So that's roughly, so it's, yeah, the canonical one is you're assuming you're in a thermal state, whereas microcanonical is something like the density of states at large value of L0. And in this case, the 2 agree, and they're both given by A over 4G. And I think it makes sense in the integrable case that that the microcanonical Cardy formula works, and you wouldn't expect it to work in the non-integrable case, just because you know, the canonical Cardy formula is supposed to be when you're with an open system. The non-integrable case is like you're interacting with a bath, and in that case, you would expect canonical to work, but not microcanonical. So it's at least consistent that microcanonical is working here. So this shows, okay, if you wanted to have integrable charges so that you have a closed subsystem, you get half of the central charge, and the Cardy formula works. And it kind of suggests that the Dirichlet form and the boundary term you use there is telling you something about kind of both systems together. But it would clearly be interesting to understand that better, or to come up with another reason why this boundary term that's sort of halfway, it doesn't correspond to a standard boundary condition that I can think of. It's not like Neumann or anything. It's something besides Dirichlet. Come up with a way to understand that boundary condition. Okay, so that's mostly the whole story. So just to summarize what we actually did here, the main goal was to carefully think about this Wald-Zoupas prescription on null boundaries, using the weakest possible boundary conditions. And it ended up, we had to generalize several aspects of the construction. And we argued for this sort of new principle in this construction of Wald and Zoupas that you should use this Dirichlet form of the flux to fix the ambiguities. Yeah, and I guess I should mention these ambiguities, it fixes like the important piece for how much is in the boundary term. And then you can employ this argument by Harlow and Wu, once you know the form of the flux, that you can fix various other ambiguities that appear in the covariant phase space formalism. So it's kind of nice that it connects to that and gives you really unambiguous definitions of your charges. Another result is this explicit expression of the central charge in terms of the anomalous transformation of the boundary term. I think it's a really nice formula, and it can be used anywhere that you're doing this sort of construction. So I think it's a nice result. And we tried to draw the analogy between holographic Weyl anomalies and this central charge. And the goal was that maybe it's the anomaly that's determining the entropy when you're doing this Cardy formula. And that might give a universal explanation for why all of these symmetry algebras seem to get the same entropy. Another thing that we did was just generalize these HHPS killing vectors to arbitrary killing horizons. It's sort of developing a picture, if you want, like a holographic description of a killing horizon. Some of the things that we did would be some steps in that direction, in particular, seeing these central charges, computing these anomalies, and also this Brown-York stress tensor that appears would be an important aspect of that. And then we found the Cardy formula gives a factor of 2, and we gave a resolution that seems to indicate that you can interpret this in terms of entangled edge modes, but it would be good to understand that better. And we showed the validity of this microcanonical Cardy formula when the charges are integrable. So just to mention some future work, I guess this factor of 2 would be the most pressing issue, and it'd be nice to see how it arises from this bracket, and in particular, if you can derive this bracket from a setup where you've glued the two subregions together. Another really interesting question, and maybe an essential piece to this whole story that we unfortunately don't have much to say about, is that the Cardy formula, if you look at where it comes from, it actually kind of has 2 inputs into it. The first is that this central charge is an anomaly. It functions as an anomaly in a CFT, and that determines sort of a Casimir energy for the CFT on a cylinder, and that's an important piece of the derivation. And the second, wait, am I still here? Yeah, sorry. The second piece is that modular invariance is employed to relate the Casimir energy kind of to the high energy or high temperature density of states. Yeah, so there's just a question of where is modular invariance in this story. It's probably true that the just Virasoro symmetry doesn't have enough information to fix the density of states, and you really need something like this bigger symmetry associated with modular invariance. But some other things you could do is you could now start looking at general null surfaces and understand where these extensions come in. Another thing that would be really interesting is to start looking at asymptotic symmetries, and this null Brown-York stress tensor, I think, would be a really interesting object in this work on celestial CFTs and flat space holography. So that would be kind of a neat thing to look into. Yeah, and I wanted to mention that this whole construction seems relevant to these recent models of black hole evaporation, where there you've got this asymptotically ADS space and you're gluing on a non-gravitational auxiliary system, but you're still doing things where you're allowing fluxes from one into the other. And so this may be a way to possibly understand how to move away from this, using this non-gravitational system coupled to a gravitational system, and maybe analyze, really characterize how the fluxes in those models work more generally, where you don't have to have a non-gravitational system. Yeah, and so there's some other things like, can you do this for higher curvature, and what exactly these HHPS vector fields and temperatures, where they come from. So yeah, feel free to ask me about that. So anyways, I'll conclude with that. So thanks.
Thank you, Anthony. So now we can move to some questions then. I can start with a quick question, actually. Anthony, do you have any, so I think first is that you're saying about using these for different null surfaces. Is there like some trouble with doing that for just regular surfaces or regular subregions in gravity?
Sorry, what do you mean by regular, or?
So I see here in future work that you're saying about you want to investigate more general null surfaces. So I just wanted to ask whether it's just a technical difficulty, or is it like to generalize these to null surfaces, regular null surfaces?
I was just saying the specific application that we looked at was a killing horizon.
Exactly. So
there's various things about a killing horizon that we used, this Rindler form, and
yep.
It just seems, yeah, it would be interesting to see, like, can you get an entropy interpretation of other null surfaces? I mean, probably, we know from holography that it's not just killing horizons, it's like RT surfaces.
Exactly, like extremal surfaces versus no extremal, yeah. Right, exactly.
Yeah, so I think it would be, presumably you could do this. I mean, another example is just like a conformal killing horizon might be a situation in a different direction where you're not even doing an RT surface, but you could probably carry out the same construction. And yeah, so it's just, yeah, if you're interested in holography on other types of surfaces, these boundary charge algebras are sort of like the bottom up way of getting at those things, and so it's just, yeah, interesting to look at. Yeah,
sounds good. Yeah, I see here Ted raised his hand, so yes, if you want to ask the question.
Thanks. Along the lines of what you were just saying, yeah. How about the horizon of a causal diamond, let's say around even a flat background? So that's a conformal killing horizon, but at the edge, it's actually like instantaneously also a killing horizon. So it seems like, I wonder if your methods would just directly apply to it.
Yeah, I haven't actually written it down. I mean, at a technical level, you just have to check how that near horizon expansion is corrected. But I think it would be straightforward, and you could just see, like, because I mean, just to point out, the original thing that we were doing with the master students is we wanted to look at the de Sitter horizon, and we sort of built everything up from there. But that's like incredibly similar to these causal diamonds, and so yeah, I would think you could try analyzing it and seeing if you get something there. I don't see any obstruction to doing that. Yeah.
Thanks. It's also interesting, just sort of a comment. When you first introduced that BT bracket, I was very uncomfortable, that it wasn't a symplectic form on the phase space of the region. And therefore I wondered, well, what should I expect the algebra corresponds to? It's not a symmetry algebra just of the system inside the region, and therefore its representations and counting of states wouldn't necessarily be counting the states just in the region. So when you came up with the factor of 2 and then proposed that for exactly that reason, it might have been a count of more than just the region, that sort of rang, well, not necessarily true, that's too strong a word, but semi-reasonable.
Yeah, it sort of works. Well, intuitively. It would be great to actually demonstrate it, though. But yeah, once we were convinced of the factor of 2, we had to come up with something. So, but yeah, I think it's plausible, and it'd be interesting to look into it more.
Yeah, so any more questions for Anthony? So then if not, so let's thank Anthony again.